Hello, this is Gareth from Creative Conners. In this short video, I want to talk to you about motor tuning today. Motor tuning is perhaps the most convoluted part of motion control, but is absolutely critical to making your show run. I like to think of motor tuning as our version of a cruise control. When you're driving in your car and you want to set your cruise control at 60 miles an hour, your car has to automatically either provide more fuel or less fuel to the engine as it goes up and down hills. Similarly, when you ask a motor to run a cue and you want it to go at a certain speed with a certain acceleration, the stagehand has to keep track of where the motor is, how far off it is from where it should be, and then it has to determine how should it apply some voltage to get that motor to either speed up or slow down to get closer to where it's supposed to be at that exact point in time. To help the stagehand do that, we have to fill in some things called tuning parameters. There are 5 tuning parameters: proportional gain, derivative sampling, integral gain, integral limit. Proportional gain is the one gain that we use most often. Proportional gain is very simple. The higher it is, the more voltage the stagehand will apply to correct for position error. The higher this number is, the faster or more aggressively the motor will try to correct its position. Derivative gain is perhaps a little weirder. You can think of it as a dampener or a shock absorber. Oftentimes, when setting proportional gain, you'll find that the motor starts to get jerky because essentially you're giving it too much voltage to catch up, and then it overcompensates and has to pull back, and so you get this oscillation or chugging in the motor. Oftentimes a little bit of derivative gain can help dampen that. Derivative sampling is used in conjunction with derivative gain. It determines how often derivative gain is applied to the motion profile. As a rule of thumb, derivative sampling should be 1 or 2 if you're going to use derivative gain at all. Integral gain is another tuning parameter that can be used to help increase accuracy. Much like proportional gain, where a higher number will increase the motor's effort to maintain the correct position, an integral gain setting of 1 or 2 will oftentimes correct for position errors at the end of travel. What this means is that you'll get what looks like a very nice smooth motion, but when you try to get that last extra inch, the motor will lurch a little bit to get there. Sometimes that's the best compromise you can come up with. One of the new features of Spikemark is that we now have 2 methods for using the tuning parameters to complete cues. This is a new box, cue behavior. It has a checkbox for strict timing mode and then a text field for target tolerance. Strict timing mode is turned off by default. What this means is that the motor will continue to run until it is within a target range. The target range is determined by the target tolerance value. So, as it is set up right now, the motor will continue to try and run to achieve target until it gets within 1/4 of an inch of the target value. If I were to turn strict timing mode on, this would revert Spikemark to use the more classic Avista behavior. In that mode, what will happen is that as soon as the time elapses for the cue to complete, the motor will be shut down, regardless of what the motor position is. Strict timing mode uses the theoretical time of the cue to determine whether or not there's a problem with the motor. So if the cue is supposed to take 10 seconds to complete but has been running for 15 seconds, the motor will be shut down. In that instance, the computer simply thinks that something must have gone wrong. Perhaps an encoder became disconnected. Perhaps the motor has stopped working. Something along those lines. Whereas in target tolerance mode, when strict timing mode is left unchecked, the motor will continue to try and struggle to get to spike, even if it's been running for 2, 3, 4 times the amount of time that it should have taken to complete its cue. We've included this as an option because sometimes it's very hard to get motors tuned properly. And sometimes it's not crucial to get them tuned well either. Having a cue take an extra second or 2 to complete is not nearly as frustrating as having it shut off 3 inches short of its target. Alright, with some of that theory out of the way, let's get started doing some actual tuning. I scoured our shop to find our worst motor. Hopefully using that motor we can see some real live tuning problems in action. I've got a single motor. I'm using the default tuning parameters. I've got 2 cues to send it to 0 into 400 inches across our stage. I'm going to load up this first cue. We are in strict timing mode. I'm actually going to load the second cue since we are already sitting at our first cue's position. Okay, I've loaded up our second cue to go to position 400, and I'm going to run this. We're running in target tolerance mode, which you can see in this indicator. We're running forward, and then it shows a little tape measure behind the arrow to indicate that we're in target tolerance mode. If we were in strict timing mode, it would show a little digital stopwatch icon. We're running and running and running. We're going to see if this actually makes it there. As you can see in target tolerance mode, the motor continues to struggle to get to position, even though the amount of time that the cue should have taken to complete is long past. This was only supposed to be a few seconds, or not even a few seconds, a 1.67 second ramp down to 0 speed, and we're taking quite a bit longer than that. But the motor's going to continue struggling and struggling until it tries to get there. Now, I don't think this motor is actually going to be able to reach its position tolerance. The tuning is so far off on this at the moment. The motor just gave up. It runs out of gas in those last couple of inches as it's trying to achieve its target tolerance. Now I'm physically pushing this motor by hand to try to get the cue to complete. So that goes to show you that in target tolerance mode, the motor still won't always complete if the tuning is way off base. Unfortunately, the tuning has to be at least somewhat accurate to get the motor to complete the cue. Now, the motor never shut off, but it still didn't have enough proportional gain to actually get to target. Let's contrast that with how the motor will behave if we use strict timing mode. I'm going to turn that back on, load up the cue to send it back to position 0, and run it. Now, what we'll see here is that once the cue time elapses, the motor will just get shut off. Spikemark doesn't know what has gone wrong, but it assumes something tragic has happened to the motor. That's why it's not on position when it should have been. And it will just stop the cue. And there it is. So we can see that even in target tolerance mode, the cue doesn't complete accurately. It tries to get there. It gets a lot closer than strict timing mode. But in either system, we're going to have to improve the tuning on this particular motor. I'm going to bring up the proportional gain to 5. Turn strict timing mode off, reload Q2, and see if we can make it to position. Oftentimes when you're tuning a motor, you'll bring the proportional gain up 1 unit at a time. If you can see that the motor is really sluggish, that it's having a very hard time keeping its motion accurate, you can certainly take larger steps, like I have here, taking it up 5 points in a single iteration. Now, we still haven't completed, although we got a lot closer to completion before the motor died this time. I'm going to double this again to 10, because we're not even close, at 5, and run this cue. When proportional gain goes too high, what you'll see is the motor starts to violently shake back and forth as it's moving. It's basically overcompensating and then pulling back and overcompensating and pulling back throughout its whole travel. Okay, and now that completes. So a proportional gain of 10 with strict timing mode turned off seems to behave fine. We'll run it in the opposite direction just to confirm. And then we'll try to run this with strict timing mode turned back on and see if the motor still has difficulty in that scenario. Okay, and that completed fine. So we're going to turn strict timing mode back on. We're going to load up Q1 and run it. Now I imagine what we're going to see is that this motor will still stop short in strict timing mode. I don't think it's running accurately enough to get to position in the amount of time that it should take. It's probably pretty close. Yep, but it stopped short. You can see we are at 6.82 inches, and we wanted to get to 0 inches. So there's a good indicator of the big difference between strict timing mode and target tolerance mode. In target tolerance mode, with these exact same tuning parameters, we were able to complete the cue. Granted, we didn't do it crisply. It still took too long on the deceleration ramp compared to what we programmed it to do, but it did complete the cue on target. In many shows, that's really all you need. You just want it to complete. You're not so concerned that it hold the timing accurately. Alright, but let's pretend like we are interested in making sure the timing is accurate. I'm going to load up the proportional gain to 15 and load Q2. And let's run that again. And that's running pretty well. Oh, but we stopped short. We were supposed to get to 400. We've stopped again about 6 inches short. So I'm going to double this number and see how we do. Let me expand that back out. Now, it's probably hard for you to hear this, but audibly, the motor's actually running very smoothly at the moment. We're not getting any of the telltale signs of too high of a proportional gain, where the motor would sound like it's starting to chug. Now, it still clicked off there at the end, but we're getting much closer to where we're supposed to be. 0.77 inches, so we're within 3/4 of an inch. Let's go ahead and bring this up again. We'll try it to 40. Now, I'm taking some pretty large leaps with the proportional gain. And one of the things that makes me feel safe about doing that is because this is a very low resolution motor. You can see here I've punched in a position scale of only 120 encoder counts per inch. That's a really suboptimal encoder. Now we got very close there. Well, not very close, but we got about 3/8 of an inch left to go. Let's go ahead and raise proportional gain up even higher. Low resolution encoders are traditionally just hard to tune. Generally speaking, you want to get as much encoder information to the controller as you can. It will make the motor run smoother, the control system works better, everything's happier with more encoder counts. We like to run around 4,000 encoder counts per unit of measurement. That gives us a real nice, easy to tune system. This, as I mentioned, is quite a bit less than that, at only 120 counts per inch. We got within 0.17 inches. That's not bad, 3/16 of an inch. Let's see if we can get a little better though. For a second here, let's just raise this up to 120 and see how that behaves. Typically what will happen at that high of a proportional gain is that we'll start to see some real lurching. Of course, it's going to make me eat my words on that. It actually seems to be doing quite well with that high of a proportional gain on this system. Oh, it's doing very well actually with that. Look at that. At 120 on the proportional gain, we got within a 1/10 of an inch. I'm sorry, 100th of an inch. That's excellent. Let's raise that up. Let's double it again. I want to see if we can get this thing to start lurching around on the stage. It's still doing okay here. I had a little funny hiccup at the beginning. Yeah, it's starting to become unstable at the end of travel. Let's double that again and see what happens. And now it is really having trouble at the beginning of the move. It was shaking back and forth as we started the move. And it'll probably shake back and forth here during the deceleration as well. Yes, indeed. And we lost our accuracy because of that shaking. Alright, so we'll reduce that back down to 120, which is where we had a nice smooth motion, and just run it back home. That wraps up our quick quick demonstration of some basic motor tuning and the differences between strict timing mode and target tolerance mode. I hope that was educational for you. Please tune in for some of our other demonstrations.